Hello and welcome to another Binder Group technical webinar. Today we're focusing on cryogenic pipe supports and the design considerations that come into play when you're dealing with low operating temperatures. I'm Riley and I'll be hosting the session, and joining me to contribute their technical insight throughout are Roger Shemilt and Brad Pearse. Roger is our technical director and he's been with Swift Metal since 2001. Over that time, he's worked with pipe supports at every stage of a project, from early design and engineering, right through to manufacturing and installation. Brad Pearse is our senior engineer. He's been with Binder Group since 2003, and 2 decades of hands-on experience with this equipment makes him our resident expert on pipe supports. He spent a good deal of that time specifically on cryogenic applications. And I'm a project consultant here at Swift. My role involves working alongside engineering teams during the design and specification stages of a project, and supporting project managers, project engineers, and procurement teams through each phase of SMP, project construction and maintenance. Let's get into it. Today we're covering 4 topics specific to cryogenic pipe supports. That is support configurations, material types, load-bearing capacities, and thermal contraction. We'll move through them in that order because each topic should give the context to the next one that we cover. Please bear in mind this is a technical overview rather than a project-specific discussion, so we will cover some higher level factors, but we won't be getting right into the weeds. However, if you do have a project on that you would like to discuss, we'd be happy to catch up on a call and go through it in detail. There will be a recording made available and there'll be some time at the end for questions, so please put these in the Q&A panel as they come to mind and we'll do our best to address them at the end. Before we look at specific configurations, there are a few things worth noting at a high level that typically narrow down the options of what can be spec'd into a project or plant, and we'll refer back to these throughout. We often end up using similar material to what is already in the plant. So where there is already installed on an existing pipeline or in a brownfields project, for example, it's common that we work with these existing standards. It's not a hard rule, but it definitely influences the selection process. Low capacity and how much movement is allowed both come straight out of your pipe stress analysis. So these are usually fixed inputs rather than choices that influence support selection. Available space on the pipe rack can rule out support options early in the process, particularly when you're working around existing steel. The direction of the load can determine whether a simple rest configuration is suitable or whether uplift or lateral restraint need to be built in. Whether it's greenfield or brownfield work shapes almost everything else. Brownfield tends to constrain our options beyond just the performance considerations. Brad, in your experience, are there any other major items that drive the configuration selection?
Yes, thanks, Riley. This is the pipe design temperature, and this determines the insulation thickness.
It's a good call out. In today's session, we're primarily looking at standardised pipe shoe configurations from the Binder range. Most cryogenic shoes which we see used in the industry and which we manufacture are variants of these designs. Are there other major configurations here that we haven't mentioned, Rog?
Yeah, occasionally we see the need for a cryogenic hanger, although that's not too common because it does restrict you in the axial movement. But it would be where structural steel doesn't allow support from underneath.
That's good. Okay, so we'll start with the BG600. The BG600 layout is the most widely used configuration which we see. It's a standard high-density puff shoe, and structurally it's designed to carry a vertical load. It can withstand some lateral or axial load. However, when these are excessive, there are usually restraints required. Where it is paired with a sliding plate underneath the shoe, this will allow the pipe to travel freely, axially or laterally on the rack. The slide plate itself removes the steel on steel contact, and that which over time can lead to corrosion. You got anything to add on this one, Brad?
Yeah, thanks, Riley. You'll notice in the photo there are two different colours of puff insulation. This is to separate the two different densities. 160 density is at the top and the 320 is at the bottom. And the main reason for the 320 is to support the weight of the pipe. The 320 is not needed at the top because there's no vertical uplift. And to use 160, it has better insulation properties.
It's good. Outside of the BG 600 configuration, the BG 601, 602 and 603 are variations that are used when the axial or lateral design loads at a given point exceed what a standard hold down or shoe guide can safely restrain. The 601 adds an extra base across the top of the cradle. So instead of relying purely on hold downs to stop the pipe lifting under load, you've got a mechanical stop built into the shoe itself. The 602 does the same thing laterally with guide bases fitted on either side, sitting right at the pipe centre line. Mounting the restraint at the centre line removes the overturning moment caused by lateral forces acting against standard shoe guides, which you would typically see used with a BG 600 configuration. And the BG 603 combines both locations, carrying uplift and lateral force throughout the cycle. The BG 615 is a different animal entirely to the 600 series. It's solving a different problem. It is a standard cold shoe rated for uninsulated pipe up to 1050 NB, and its main function is to provide a thermal break between the pipe and the structural steel underneath. Instead of an insulation package, it uses a single load-bearing isolator. This has a typical standard thickness of 70 millimeters and sits between the pipe shoe and the steelwork. There are a few different materials that are considered as the load-bearing elements for this configuration. Some of the more common brands we see used are Pamali, Durastone, Asplas, and Micarta. The selection here usually comes down to project-specific factors like company specification standards or project preferences. Where you'll see the 615 used is on lines where the pipe itself is intentionally left uninsulated. Exhaust lines are a classic example because thermal loss from the pipe isn't so much of a concern for the process. What is a concern here, though, is what happens to the structural steel supporting it if there's no isolation at all. Sustained cold contact will embrittle and weaken the steel over time. So the 615 helps to break that thermal path without the cost and complexity of a full insulation system the pipeline doesn't need. The AeroX support is a relatively new entrant to the market, and final thermal testing in accordance with NORSOC standards is underway at present. It's been designed to allow full system use of aerogel insulation, and we'll come back to this in a few minutes. The fundamentals don't change. It doesn't introduce a new set of configurations of its own. It gives you the same restraint options as the BG 600 series, rest, uplift, or lateral. So functionally, the decision tree is identical to what we've just walked through. What does change, though, is the footprint, because AeroX pairs aerogel insulation with purpose-built load-bearing component. Rather than a larger puff cradle, the whole assembly sits smaller and lower than the equivalent BG 600 series shoe for the same pipe size. This can be beneficial on a congested pipe rack or anywhere wind loading on the support is a real consideration, say in offshore platforms. AeroX isn't a replacement for the 600 series conceptually. It's more the underlying logic in a smaller package. The configuration decision itself doesn't change. What you're really weighing up is whether the existing insulation space or wind loading require a smaller support. There are two categories of material we're looking at today. Firstly, insulating materials. We'll cover here puff and aerogel, and then alternative load-bearing materials, being Durastone, Pamali, and other resin and epoxy-based elements. Puff does a reasonable job of both. It insulates and it carries load, which has traditionally made it a default material used in these systems for over 50 years. Puff's operating range covers the full span you'll typically deal with in cryogenic service, from negative 196 right up to 100 above. So it's suitable across LNG duty, most industrial gases, and the milder end of the cryogenic spectrum. It comes in 3 common densities, and the trade-off between them is fairly intuitive once you see it laid out. A lower density gives you better thermal conductivity, meaning better insulation performance, but it's a softer material with less inherent strength, so it doesn't carry as much load per square metre of contact area. That's why insulation thickness is driven by the pipe's design temperature rather than by load. You size the insulation for the thermal job it needs to do. If the load then turns out to be more than a lower density material at that thickness can support, it can be addressed by either lengthening the shoe to spread the load over more bearing area, or by adding additional load-bearing components into the assembly. Every 5 years, we get a BG 600 650 MB cold shoe tested as a requirement for supplying cold shoes to major EPCs. The test involves taking a pipe down to cryogenic temperatures and maintaining it for several hours. While at this temperature, we run a series of tests, some to our own standards, some are also required by our EPC clients. One of the key measures we take is the thermal conductivity factor, or the K factor. This tells us whether the puff insulation is doing its job, which is to sustain the cryogenic temperature inside the pipe consistently. Afterwards, we send the puff off to a lab for destructive testing, and this includes closed cell content, compressive strength, water absorption, and flammability testing. Installation is where a lot of the long-term performance of the puff system is affected. The single biggest rule in cryogenic shoe assembly is that everything has to stay dry. Moisture ingress during installation will turn to ice and ultimately destroy the foam and degrade the insulating capacity. This has major implications, both from an efficiency and safety standpoint. As the pipe cools and contracts circumferentially, you need contraction gaps built into the puff, and these get packed with a fibrous insulating material to maintain thermal continuity across the gap. Disc springs on the clamping bolts do the mechanical work of keeping constant clamping pressure through that entire contraction cycle. So the cradle stays tight, even as the pipe and insulating material contract inside it. If there's one thing worth flagging above everything else, it's the vapor barrier integrity, both within the support and the rest of the system. In our experience, that's where the majority of field failures originate. A compromised barrier lets moisture in, and from there it's only a matter of time before it becomes a serious problem. On the load-bearing side, permalloy, a densified wood material, is the one that you'll see most often, largely because it's well proven, although it does need some ongoing inspection and maintenance over the life of the asset. Durastone is another option. It's impervious to moisture, which makes it a genuinely lower maintenance option by comparison, and both install in sequence with the puff wedges surrounding them. Roger, can you tell us about this one?
Yeah, no worries. This is just a prime example of what happens when water or vapor is allowed to breach the insulation. So you can see ice has formed on the pipe. It's ended up in catastrophic failure of the insulation, and the pipe has actually dropped inside the support, which creates a structural and mechanical problem as well.
It's good. We often get asked for advice on customization of cryogenic pipe shoes. In fact, the majority of supports are modified in one way or another to suit project requirements. This was a project we were involved in a while ago. Rog, can you take us through this?
Yeah, sure. This was where there was a weld seam on the pipe that was protruding, and the insulation, being a rigid product, needed to be modified. So we actually were able to help the client create a cavity or a recess to make way for the weld, but then that cavity needs to be filled with a fibrous insulating material, and the raw edges, cut edges of the insulation need to be sealed properly. That's just an example of the sort of modifications that can and do happen.
Thanks, Rog. Aerogel is a next generation insulation that covers essentially the same cryogenic operating range as PUF, but its thermal conductivity sits in a completely different league. It delivers a significantly better result than any traditional insulation. However, due to aerogel not being load bearing, it's a key difficulty up until now has been that there's no satisfactory way to support cryogenic pipe work without a compromise either structurally or thermally. We developed the BG700 AeroX support at the request of the manufacturers and installers of aerogel insulation. We work specifically with the Arizasil 650 blanket, which is a third generation aerogel technology. The support incorporates separate load-bearing components which are thermally efficient at cryogenic temperature, and critically, they carry substantially more load than a traditional PUF shoe. This has allowed aerogel blanket to be viable as a system-wide insulation material. The installation process with aerogel is quite different to PUF, and mostly in ways that make life easier on site. It comes as a flexible pre-manufactured blanket, and it is installed in layers up to a thickness of 80 millimeters, which is wrapped and taped around the pipe rather than rigid molded halves. So there's considerably less trial fitting involved than with a PUF shoe. Pre-formed load-bearing support rings will go in sequence as the aerogel is installed. One of the critical parts of this is the vapor barrier. The vapor barrier that's paired with the aerogel is a self-healing butyl-backed mylar with considerably better puncture resistance than a standard vapor film. And disc springs do the same clamping job as they do in PUF. They maintain the pressure through the full thermal cycle. Depending on the pipe size, aerogel support systems can provide up to a 69% reduction in cross-sectional size, and this makes them lighter and easier to install. Pipe shoe design load ultimately comes back to the pipe stress analysis data. Specifically, three things have significant impact on the load requirements. These are spacing, pipe size, and movement. There are three ways we typically see higher load requirements solved for in practice. You can lengthen the shoe, which increases the bearing area carrying the load. You can layer in a higher density PUF, which is what Brad showed us earlier. This will have a better compressive strength, but it will impact on the thermal performance. Or you could pair the shoe with Permali or Durastone wedges or higher density material wedges, which will bring in a structural material to take the load alongside the PUF insulation. Thermal movement on a cryogenic line acts in three main directions. We see circumferential contraction, which being the pipe shrinking around its own diameter as it cools. Axial movement with the growing and shrinking of the pipe along its length, and then lateral movement being displacement across the rack perpendicular to the run itself. Supports are designed with these three variables in mind. Just on this slide, Brad, I'm noticing there's clear plastic over the shoe in this picture. Have you got any comments to make on that?
Yes, Riley, we purposely added this photo to show you that black plastic that is UV resistant, as it must protect the PUF from UV damage.
It's a good call out to make. First on circumferential contraction. So at a mechanical level, it's managed the same way, regardless of what insulation type you're working with. Disc springs are torqued to the required specification, keeping the clamping pressure constant as on the cradle as the pipe contracts beneath it. Getting that setting right is critical to maintain contact and to uphold the thermal performance of the system. Where puff and aerogel genuinely diverge is in how much they contract relative to the steel pipe underneath them. Puff has a noticeably higher coefficient of contraction than steel, so as the pipe shrinks, the gap closes in the insulation. And as we saw earlier, these gaps have to be accounted for with contraction joints, which is usually filled with a fibrous insulating material to maintain thermal continuity across them. Contraction joints like this are also the point we flagged earlier as most exposed to moisture ingress, which is why joint inspection is so critical on a puff system. Aerogel largely sidesteps that problem because its coefficient of contraction is almost identical to steel. This means regular contraction joints aren't required. The thing to get right here, though, is offsetting the sequential layering to ensure there's no direct path for cold creep. Axial and lateral movement are addressed with different hardware to circumferential contraction because the movement is external to the pipe support. We're managing the pipe physically sliding as it expands and contracts along its length or shifting sideways under load. As with standard shoe configurations, slide plates sit between the shoe and the rack and let the pipe travel smoothly, axially or laterally. Movement where there is bare steel on steel contact is higher friction and increases the resistance to free pipe movement. It also causes significant wear over time and lead to a premature replacement of the support system. A slide plate keeps friction low and helps to extend the working life of the shoe and reduce excessive stress on adjacent components of the pipe system. Guides are designed to constrain movement in one direction, providing minor lateral restraint without locking out that pipe axially or laterally altogether. If there's one thing to take from today, it's that a cryogenic pipe support design is rarely a catalogue pick. There are genuinely large range of variables at play, the configuration, the material, the load, movement, and by the time you've worked through a real project, almost every support system has something about it that's been customised to the client or EPC requirements. As specialists in this field, we're always glad to work with you through that design process, but every project brings its own combination of constraints. What we've covered today is meant to help inform that process in a broader sense. That said, some patterns hold across most projects. Configuration is mainly driven by what's already installed on site, space available on the rack, and the direction of the load you're designing for. Material choice is often dictated by existing plant standards, the operating temperature you're working to, and project-specific specification requirements. Load data is something we always have to work with, and it's typically what decides whether a standard shoe is enough or whether you need a reinforced configuration or load-bearing material, such as permalloy or durastone alongside it. And movement often gets accommodated within the support system itself through disc springs, contraction joints, slide plates, hold downs, and guides. That's everything from us for the formal part of today. So we'll cross over now to some questions that have come in as we've gone through the session. We're also going to launch an anonymous poll, and we'd greatly appreciate your feedback on this session. And please send in some suggestions for the next thing you'd like to hear from us. Okay, across to some questions there. Rog, we have had one come in here on specifically to line stops for insulated cryogenic systems. You got some comments to make on that, Brad or Rog?
With a line stop or an anchor, there's two parts to it. So we have to anchor the support to the pipe. So there's got to be a mechanical stop inside the pipe. And then the pipe shoe itself has to have a mechanical, sometimes it's bolted, sometimes it's just via a line stop on the shoe to create that, if you like, mechanical interference to restrict the axial movement of the pipe. But it requires components inside, so site welded to the pipe and incorporated into the pipe support as well. We'll typically have high density load materials inside the support to withstand the thrust, any thrust loading.
Was there an example a while ago there, Brad, that just trying to recall here, where we used a Permally material inside the pipe shoe as an axial stop or restrictor? Probably a couple of years ago, but
generally we can use puff as an axial stop, but when the axial load gets, I guess, above the operating limits of the puff, then we can use like a Permally or an Asplas or a Durastone material.
Yeah. There were a couple of questions that actually came in ahead of this session. One of which I've just got here. So when cold shoes are installed, they need a Foster product 9066 to seal around the puff and pipe. Does Swift provide this? Rog?
Yes, yeah, everything needed for the install and supply of the support is typically included, whether that's the vapor barrier, the sealant product, or the insulation itself. That'll all be included as part of the kit, typically.
It's good.
That Foster's product, that sealant does have a pretty short shelf life. So that is a consideration if those supports are going to be on site, stored on site for any length of time.
It's helpful. I've had a few more come in specific to the axial stop requirements. Wondering whether it might be worth doing a white paper and circulating on that after this. Do you think, Rog and Brad?
Yeah, absolutely. If that's a trending question,
seems to be one that's come in a few times. We'll circulate that as part of sending out the deck and the recording. There is one here actually for chilled water lines with temperature of 7 degrees Celsius. Do we require to insert fiberglass between the two puff halves?
Generally, no, because the temperature is not quite low, but I guess it would also depend on the actual piping engineer's design requirements. So I guess to avoid any risk, then you can add some fibrous or Textrafine or a certain material in the gaps.
Yeah, I guess would Textrafine there be probably the more common one that we'd see used, Brad, do you think? Or is there other?
Yeah, Textrafine is probably the most common. There's also foam products, but Textrafine's the most common.
Yeah. Insulation thickness on this would be, you're not dealing with the same cryogenic temperatures either.
No, probably about 15, 20, at maximum, and also like a low density. So 160 for even less.
Depending on the pipe size, yeah.
Yeah.
Mm-hmm. Okay. Well, we will address that axial stopper question that's come up as a separate paper, but that's pretty well concluded all the questions that have come in through the course of the session. So I'd like to thank everyone very much for your time and for joining, and make sure to keep an eye out for our next webinar. Send in some suggestions of topics you'd like to hear us cover off on, and have a great day. We'll see you next time. Thanks all.
Thank you.
Thank you.